This is going to be the lecture over chapter 12. It's really not going to be too much that goes on with this that we will need to cover, but I want to hit the main points because I think these are the most salient things that you need to be able to take away from how things operate in a clinic in a modern setting. Basically, treatment planning nowadays is going to require accurate patient data acquisition, such as external body contours and internal anatomy. Now, sometimes, there are several different ways that that can be accomplished. Primarily today, what we are looking at is taking a CT scan of the patient. That is usually how things are done. Most centers nowadays are going to have a CT scanner or have access to one. Once the CT is taken, then the data will be loaded into the computer, the planning system, however it's transported. And then once it's transported there, what we're going to do is we're going to take that data and we're going to figure out how to configure what it tells us so that we can go through and we know how to determine what dose needs to fall in certain spots. Now, in days before, we had manual devices for body contouring, like a solder wire, which you can lay over the head or something like that to give you an idea as to what the shape of this is like. Pantograph type contour plotters, electromechanical devices. Those are old ways of doing things. We're not going to cover those here because, quite frankly, that is a waste of your time. So the CT numbers are going to bear linear relationship with attenuation coefficients. And what that means is that the CT numbers depend on electron density as well as atomic number. So if the scanning beam is kilovoltage X-rays, or if, let's start again. The CT numbers depend on electron density as well as atomic number if the scanning beam used is kilovoltage X-rays, as in conventional CT scanners. What we're going to do is we're going to take a correlation between those CT numbers and the electron density. And the way we do that is we scan a phantom of known electron densities in the range that include lung, muscle, and bone. That way the CT unit is calibrated. So we know how certain densities should be interpreted. Once that information is assembled and is transmitted over to the planning system, we calculate it from there. Image modalities such as ultrasound, which is used primarily for prostate, or at least used to be. MRI and PET are useful in mapping out structure and functional anatomy, but their signal values are not correlated with electron density. So in other words, what you're getting there is not going to correlate with electron density, and electron density is what we need for the algorithms that we use in order to calculate dose. So fusion techniques are used to combine their images with our CT that we took to provide geometric accuracy of external contours in internal anatomy. In other words, and I'll show you pictures of this later on. What we'll do is we'll take an MRI or a PET CT and we'll register or merge that with the CT scan that we take. And with that, you can determine, oh, maybe this is part of the GTV or the gross tumor volume. Maybe this is clearer than I thought, so we won't hit this area. Accelerator mounted accessories such as EPID and cone beam CT systems allow treatment verification before and during treatments. These capacities are essential when using conformal radiation therapy techniques, 3D, and IMRT. Most of your clinics right now are going to have some form of EPID or CBCT, KVKV, megavoltage, MV orthogonals, that kind of thing. And most of them are no longer going to have you shooting this on film. They're going to have an onboard imaging process for you to be able to shoot, to take the image and then determine whether or not you're on target and whether or not you want to yell at your dosimeters for not having the bones showing up as well as they should. Not that that's ever happened to me. There are methods of contour and tissue heterogeneity corrections. They're somewhat empirical and have given way to computer algorithms. In other words, there are certain methods within the system for treatment planning in which we can go through and we can determine, how different are the electron densities within the patient. And so there are certain correction-based algorithms. And the most sophisticated algorithms are model-based, in other words, pencil beam, convolution / superposition, and semi-Monte Carlo techniques. The ones that they're talking about here, the old methods, and you use these primarily when you go through and you check to make sure that the number of monitor units that you compute are fairly close to a second method by which you go through and you evaluate those. And let's see if we can find these methods here. They're not present here. Okay. Could have sworn I saw them earlier. Let's see. There we go. These are some of the things that we have come across. There are methods, namely the TAR, ETAR, and generalized batho for using a heterogeneous phantom containing layers of polystyrene and cork. The TAR method overestimates the dose for all energies. The ETAR is best suited for low energy beams. The generalized batho method is best in the high energy range. So you've got several different methods for trying to determine what the electron densities are. We'll probably have a question on exactly which ones those are, because they're not going to ask you during the registry how to go about doing that, but knowing what they are is probably worthwhile. Let's see, dose within bone depends on beam energy. Dose to soft tissue within bone is 2 to 5 times higher in the orthovoltage and superficial range of beam energies. It's about 3 to 10% higher in the megavoltage range when it's used clinically. Dose reduction can occur at air cavity surfaces and lungs due to a partial loss of electronic equilibrium. In other words, the number of electrons that you have in something that is solid is going to be different than what you encounter in the air cavity. And so the electron density, or the electronic equilibrium, meaning that you gain an electron for every one that you lose as far as scatter goes, that can hold whenever the medium doesn't change very much. But when you get into an air cavity or you're adjacent to an air cavity, that assumption is no longer valid. The most prominent effects is for small fields, as you might imagine, and high energy beams. Compensators are used to compensate for missing tissue at the surface or internal inhomogeneity, such as the lung. They're designed to take into account the extent of missing tissue. Compensators to surface distance and the density of the compensating material. In other words, what you are attempting to do here is, let's see if we can find it. You're wanting to try to smooth out whatever surface it is that you're encountering. And so one way to do that is to build a compensator that you would put over the patient. And therefore, when the beam does interact, it almost feels like it's a flat surface. And then reproducibility and stable patient positioning, proper mobilization, accurate measures of external and internal bony landmarks. These are all crucial elements of radiation therapy. To give you an example, one of the things that we have at the clinic at which I serve is a tumor loc. Basically, if the physician knows what they want to treat to, they will take they'll tell one of the computers there, hey, I want the isocenter marked at this spot. Well, that information is then logged into the computer and then sent over to me. It's kind of like a lap laser where you establish where in the patient you want the beams to set up. And so you send that information over, and that allows the dosimeters to be able to line up to that particular spot without having to pick an isocenter on their own and tell the therapist what the shifts are from some other established point. A more low-tech way to do this is to put leveling BBs as well as an AP BB and try to get them all in the same plane, which almost never happens. And the point at which they intersect is going to be your origin, and then you shift from there. So they can line up to where that is, wherever that those BBs are, and then you can make a shift from there. Obviously, stable positioning. One of the pictures that they do have here is a bite block system for head and neck. If you have the bite block in there, it's an attempt to try to make sure that the jaw is in the same position. And a lot of times this bite block might be used in order to separate the tongue from the roof of the mouth in order to be able to not damage the tongue, but hit the roof of the mouth, if that's indeed what is problematic. So it tries to save the tongue a little bit, but you want to make sure you do that every day. So this is a type of setup that you can rig in order to be able to try to accomplish that. Other things that you probably run across there, vac bags, alpha cradles, things of that sort, to try to make sure that a knee sponge, try to make sure that you can line up the patient in the same position every time. And so that's what that's about. So that's a lot of chapter 12. There are some key points in there that we can kind of go over a little bit more in depth in another video, but that's the summary of the chapter. We'll see what problems I can manufacture for you out of this.